We've looked at situations like this before. You remember these? This is called a modified Atwood's machine. And we saw that, let's assume there's no friction here. We saw that the acceleration is directly related to the net force, that would be the weight of this, and inversely proportional to the inertia of the system, the mass. Okay, assuming there's no friction. Well, actually, even if there is friction, it's the net force. So let's say there's no friction here, and the net force is just the weight of this. What about a system where we have rotation going on? What's the rotational equivalent to this? Well, there would be an angular acceleration instead of a tangential acceleration here that's going on. And so that angular acceleration would be caused by a torque net instead of an F net, and inversely related to the rotational inertia. But how do we calculate this rotational inertia? What is rotational inertia even? So we have the relationship that the tangential acceleration is equal to R alpha. And let's start off with the acceleration is directly proportional to the net force over the mass, the inertia. And if we plug in R alpha for the acceleration, we get the following. Keep in mind we just found out torque is the force times the distance away from the pivot point times the sine of the angle. Let's assume the angle is 90 degrees for a maximum, and so that means the net force would be proportional to the net torque divided by the lever arm, the radius, away from the pivot point. Let's plug that in for the net force, and we get the following relationship. And if we solve this for alpha, we get the net torque over mr squared. So compare that to over here, that means that the rotational inertia is somehow related to mr squared. It's actually the sum of mr squared. But what is rotational inertia? It's a measure of how much resistance there is to a rotational status. So if something's already rotating, it's how hard it is to get it to rotate even faster or to slow it down. And to give you an idea of what it feels like, what you need to do is stop this video and grab yourself a pencil, a fresh, brand new pencil, not sharpened, and balance it on the razor end on the end of your finger and try to notice how hard it is for you to do that. You'll see very quickly it's pretty hard to do. Now try to do it with something much longer, like a meter stick in length. You'll find out that it's much easier to balance it on your finger. You can move your hand underneath it. You'll see it's much easier. In fact, to make it even easier, if you put a wad of clay at the very end, the opposite end of the meter stick, it becomes even easier. So it has more rotational inertia. It's lazier. It doesn't want to change its rotational status. And therefore it gives you more time to adjust your hand's position underneath it to keep it balanced. So rotational inertia depends upon the mass distribution with respect to the axis of rotation. And so we just said that I, the rotational inertia, is equal to the sum of mr squared, or in calculus terms, it's the integral of r squared dm, where dm is the individual mass element that you're summing up. If we're talking about like a ball and an end of a string, it's just simply mr squared. If we're talking about a hoop, that's also equal to mr squared. If we rotate the hoop kind of like spinning a coin on your desktop, that's 1/2 of mr squared because the mass is closer to the axis now. By the way, all of these rotational inertias you don't have to have memorized. Sometimes on the AP test you have to derive them. For instance, these are the only two that you might have to derive. Let's say we have a stick that you rotate about one end. Its rotational inertia is 1/3 ml squared. If it's rotated about center, that's much easier. It has less laziness. It's 1/12 ml squared. Sometimes these we have to derive. For a solid sphere, the rotational inertia is 2/5 mr squared. For a hollow sphere, like a basketball, it's 2/3 mr squared. So more of the mass is further away from the axis of rotation, so it's lazier than a solid sphere. And if it's a cylinder, it's 1/2 mr squared. So it's a little bit lazier than a solid sphere. Okay, so I told you there's only two that you sometimes have to derive on the AP test. So they're either given to you or sometimes they'll ask you to derive it and you'll have to use calculus. So let's do that for this one here. It's 1/12 ml squared. That's what we know the answer to be. Let's see how you would derive that using I equals the integral of r squared dm. So we're going to integrate from one end to the other end. So that would be from negative L over 2 to positive L over 2. dm would have some density, let's call that lambda, or which would be like a mass over a length. So it has some density times the width of it, which is dr. Let's plug that in for dm. Let's assume this is a constant density, lambda, so we can factor this out. And now we can integrate r squared with respect to dr. Integrating this, also remember, again, lambda is just simply the mass density, which is mass over length. And now integrating this, we get r cubed over 3. We're summing up from negative L over 2 to positive L over 2. So we end up getting the following relationship. So combining this together, we'll get ml cubed over 3 times 4, which is 12L. The L cancels, and we are left with 1/12 ml squared. So this is one of the things that you might have to do on the AP test, derive this. You might also have to derive the relationship for when it's about its end using what's called the parallel axis theorem. So let me back this up again. Notice the axis, it was spinning about the center, and now we're shifting it some distance h all the way to the end. What we're going to use is what's called the parallel axis theorem. This is something else you really need to make sure you understand because it's pretty easy actually. And what it says is I through any parallel axis, so the rotational inertia through any parallel axis is equal to the rotational inertia about the center mass. That's what we found just a second ago, 1/12 ml squared plus m times h squared, where h is how far we shift that axis. Well, in this case, we shifted at a distance L over 2. So we have to square that. Again, m is just the mass of the entire thing. And so we get the following. Common denominator would be 12. So that second term would be 3/12. Combine this, and we get 4/12 ml squared, which simplifies to 1/3 ml squared. So this is the equations we have so far. So most of these angular kinematic equations and the dynamic equation we have so far, these are ones that look very similar to their linear counterparts. So those, I don't know that I'd spend a whole lot of time memorizing those because those are pretty straightforward. It's these ones in the middle that are pretty important. And we just added two more. The rotational inertia is equal to integral of r squared dm. And the parallel axis theorem says that the rotational inertia at about any parallel axis is equal to the rotational inertia about its center of mass plus md squared, where d is how far you shift that axis. And then we already have the torque equation.